Okay, so I'm assuming these three vectors are linearly independent. I checked, one's in this direction, one's in this direction, and one's kind of out that way. So I don't think they're all in the same plane. So what I want to do now is I want to take this direction, and I want to compress space perpendicular to this direction by a factor of 2. In this direction, I'm going to stretch it, okay? I'm going to stretch it by a factor of 3. And in this direction, I'm going to invert it. I'm going to multiply it by -1, okay? How do I do that? How do I get a transformation that does that? I make these eigenvectors. This one with eigenvalue 1/2 to compress in that direction by a factor of 3. This one with eigenvalue 2 to stretch by a factor of 2 in this direction. This one with eigenvalue -1 to flip things relative to that direction. Now what that does to the whole space, you know, if we did that, the space that we're in, how would we get turned inside out and inverted? Okay? What would happen to us? We get stretched, and you know, it'd probably be painful. Okay. So I'm going to say these are eigenvectors. With respective eigenvalues (1/2, 2, and -1). Okay? So what's your matrix for transformation with respect to B?
All right, real quick, let's go over this. So the first was dwarf rhododendron, galax, number 2. Oak hydrangea was 3. Prickly pear.
Okay?
5 was
Well,
judd. Dog apple. 7 is New York fern. 8 was tag owl. Number 9 is Appalachian hill cane. 10 is broadleaf arrowroot. 11 was the Turk's cap.
x1, x2, x3 with respect to B means the vector x1, v1 plus x2, v2 plus x3, v3. So if I want to do vector, or the column vector 5, 2, -4, I'd take 5 times this, add it to 2 times this, and then subtract 4 times this. Okay? That's what it means. Okay, well,
So let me just kind of tell you guys where we're at. So at this stage, you're done with quizzes.
what's your transformation of V1?
So all those grades have been put in.
The transformation of V1 is an eigenvector with eigenvalue 1/2, and what's T of V1?
We also added
What's an eigenvalue and an eigenvector mean? If an eigenvector has eigenvalue lambda, when you transform it, it becomes the same vector but multiplied by lambda. It's a solution to A of V equals lambda V. That's the definition, okay? And that's the intuitive idea. It just takes V1, it gives you 1/2 V1. What's T of V2?
2v2?
Again?
2v2?
Yeah.
once I get them all, right? It's not that you want to do something.
And 2 V3 will be negative V3 since the eigenvalue is -1. Okay? Didn't need to close that parenthesis. So what's T of x1 v1 plus x2 v2 plus x3 v3?
1/2 times 2 1 negative 5 plus 2 times 3 2 4.
I'll write it. Is x1 times T of v1 being 1/2 v1, right?
Mm-hmm.
And I can do that by the linearity of the transformation. Okay? That's x2 times 2v2 plus x3 times negative v3
All right, so that's where we are. All right.
So it's this, right?
We're going to go out and
I mean, I just, you know, this is obvious, okay? So if you look at it, you'll see. So how would I write this as a column vector with respect to V? And I said V, it's B, kind of rhymes. Okay, so what I fill in there?
1/2 x1, 2x2.
Exactly.
and negative x3.
Because the representation with respect to B just tells you what multiples of V1, V2, and V3 we get over here. Okay, so that's going to be, I didn't make my brackets wide enough, or I'll have to write small. 1/2 x1, 2x2,
Hey, that's a great question.
and negative x3. Okay? Okay, so, well, so now we know that T is represented by matrix A and I should say so relative to the basis B,
All right, guys, hold, let's see.
A has to multiply x1, x2, x3 and give you what the transformation gives you, which is 1/2 x1, 2x2, negative x3. Okay? Just to be grammatical.
All right, so did you guys get that? 10:30.
So what is the matrix A?
All right, let's go down there, let's knock out this.
1/2 2 1. No.
Well, if it was 1/2, 2, negative 1, it would just have one row, and it would give you 1/2 x1 plus 2x2 minus x3. It wouldn't give you a vector.
Yeah.
It gives you just a number.
Yeah.
So it would have to be the dot product.
Well, no, let's see, A is going to have rows. How many rows is it going to have?
3.
Huh?
3?
Why 3?
Because there's 3 x's.
Because what?
Because there's 3 x's.
Because there's 3.
3 x's.
You mean here?
Right.
No, that's not why.
Because that'll make it a square matrix.
Didn't say it had to be a square matrix. It does kind of follow from what I've said, but you haven't proved it, so I'm not gonna let you say that.
Right.
No offense. Okay? Well, the fact that you got 3 of them here does tell you something about the matrix, but it doesn't tell you it has 3 rows.
Tells you it has 3 columns. Because you can only multiply.
Yeah, well, why does it have 3 columns?
Because you can only multiply it by a matrix that has 3 rows if it has 3 columns.
Why?
Because that's how you multiply matrices. You multiply rows by columns.
Oh, you multiply rows by columns.
Yeah.
Okay, that you can say. Now, since you can multiply rows by columns, and you know perfectly well why, but since you can multiply rows by columns, how does that tell you that this matrix has to have 3 columns?
Because the other one has 3 rows.
That's a little bit incomplete. You haven't made the connection. Now, I'm trying to get you to make connections because that's what you have to do to solve problems correctly, okay? That's what we're doing, okay? So we know that you got to multiply rows by columns, right? So what does that tell you about the rows of the matrix? And we got to multiply the rows by this, right? So what do you know about the rows? Well, what do you know about rows and columns? When can you multiply rows and columns and when can't you? I'm dragging this out. We don't need to do that in camera.